Okay. Rhombi, squares, maybe even trapezoids. That's what we're going to talk about. All right. So we have some properties. Oh, I see. Maybe I might mess myself. Diagonals are perpendicular in a rhombus. And now we have that. So if we have a rhombus, we have right angles. We have a rhombus, we have right angles. Okay. And a parallelogram is a rhombus. The diagonals bisect the opposite angles. So, see, those angles are congruent, and these angles are congruent, and so are these. Okay, and even, yeah, 5 is congruent to 7, 6 is congruent to 8. Lots of congruency there. And so, so I had already started to do this here. You can see the remnants of the Pythagorean theorem. And why would those be there? Because since the diagonals are perpendicular, we have a right triangle. So I was actually looking at guided practice 1A, and FK is 5, so we can put a 5 up there. And then FG is 13. We can put a 13 right here. Bring it out. 5 there, 13 here. Pythagorean theorem time. We can figure out GK, right? This is GK. And if we do that, here's the thing. So we can figure out GK, but we figure out GK, we know that it's congruent to KJ. And why is that? Because the diagonals bisect each other. Of course, because it's a parallelogram. A rhombus is a parallelogram. Okay, so you can go and you can do that. The Pythagorean theorem. And then also this one right here, JFK and KFG. Let's find those angles in the picture. JFK is, that's angle JFK. And KFG is right there. Well, we know from the theorem we just looked at that they are congruent. So angle JFK is congruent to angle KFG. And I'm even going to put my theorem number here. So I can start memorizing the theorems. And that would be theorem 616. Theorem 616. All right. And because they're congruent, the expressions can be set equal. 6y plus 7 equals 9y minus 5. And on you go. All right. The square is a parallelogram with 4 congruent sides and 4 congruent right angles. All right. Now, here's where I got stuck for a second. Now, where was you're right here. I got stuck right here, but I shouldn't have. Okay, we're gonna write a proof that SQ is perpendicular. Okay, SQ is the perpendicular bisector PR. So we know that's 90. SQ bisecting, and then the other way around too. All right. So what we know is, that's what we know. But then also we know that RMS is isosceles, which means that SM is congruent to RM. So actually we can take off these 2 hash marks and just make 1, because so they're bisecting each other, but we also have an isosceles triangle, so we know that all 4 of those little diagonal pieces are exactly the same. And if that's true, then so our proof plan So I'm not going to write the whole proof right now. I'll just make the plan, and you can try to write the proof and bring it to class or post it in the organizer. But the proof plan would be this. Well, we know that in a rectangle, quadrilateral is a rectangle if and only if the diagonals are congruent. Do you see that the diagonals here are congruent? Are they congruent? They are. And it's a rhombus if and only if the diagonals are perpendicular. So here in this figure, we have congruent diagonals and we have perpendicular diagonals. And how can we say that they're all congruent? Well, we know that we have bisectors. So we have bisectors, and then we have isosceles, the definition of isosceles, and then there's going to be the transitive property to say that SM is congruent to MR. Then once we know that, we can say that the diagonals are congruent, and the given was that they're perpendicular. So then we can say, congruent diagonals. That means we have a rectangle. We can say perpendicular, and that's a theorem. And the perpendicular diagonals, that means we have a rhombus. And if we have a rhombus and a rectangle at the same time, by the theorem that I just read, I read a theorem about this. Where was that theorem? Did you guys see that theorem? Conditions for a rhombi. 620. If a quadrilateral is both a rectangle and a rhombus, then it's a square. So we're proving that it's a rectangle, congruent diagonals, it's a rhombus, perpendicular diagonals, it's a square. Pretty cool, huh? All right, Kathy is designing a quilt with blocks like the one shown. If she marks the diagonals of each yellow piece and determines that each pair of diagonals is perpendicular, okay, Kathy, you have perpendicular diagonals. She can conclude, can she conclude that each, well, if the diagonals are perpendicular, then it's a rhombus. Isn't that right? Oh, if they're perpendicular bisectors, then it's a rhombus. So do we know that the diagonals of each piece and determines that each pair of diagonals is perpendicular? So we have to say, no. No. She must also show bisecting, right? Because there are other figures. If you had perpendicular, you could have perpendicular like that, and that is definitely not a rhombus. Perpendicular diagonals, but not a rhombus. Does anybody remember what kind of example this is called? This is called a counter example. From back in October. It only takes one example to show that something's not true. That's called a counter example. If all four angles of the green piece have the same measurement, and the bottom and left sides have the same measure, can she conclude that it's a square? All four angles of the green piece have the same measure, and the left sides have the same measure. Yes. Yes, because all four angles congruent, that means it's a rectangle. And a rectangle with perpendicular diagonals is a square. So the only difference between a square and a rectangle is those perpendicular diagonals. That must be a thing. A rectangle with perpendicular diagonals is a square. Diagonals are perpendicular, it's a rhombus. There you go. Okay, well, I'm not gonna search through this and just waste this precious video playing time. But not here, should be here. I can prove it to you. All right, so that is rhombi and squares. And now we are going to, oh, maybe it was in the section on rectangles. Trapezoids and kites. All right, isosceles trapezoids. I actually put the properties of isosceles trapezoids in a song because, you know, it's always the last section in the book. And, you know, you just watch the whole section, you're probably, you know, losing some capacity. But hey, trapezoids are important. They're like the first generation quadrilateral. They're all over the place because even everything that has one pair of parallel sides, that's a trapezoid, right? So they're abundant and they have properties that we can do. So first of all, let's know that a trapezoid has two bases and the legs are the other sides. An isosceles trapezoid has congruent legs. Leg one is congruent to leg two. And the base angles are congruent. If it has one pair of congruent base angles, it's a trapezoid. Oh, congruent diagonals. Okay, so not just rectangles, but also isosceles trapezoids have congruent diagonals. My diagonals are congruent, and so are my legs. The other trapezoids are rotten eggs. All right, and so the speaker is an isosceles trapezoid. This cafeteria plate is an isosceles trapezoid. And so we're going to put the measurements in here, and then we're going to know all the other angles and sides because of the property. Okay, so we have isosceles triangles above and below the diagonals, congruent triangles here, congruent legs there, and we have alternate interior angles, vertical angles. Okay, so YZW 45. Oh, this triangle right down here is isosceles, so that's also 45. And alternate interior angles means that's 45, and so is that. All right, see? And then, so that's 90. So then this must be 90. Right? And then 290, so this gotta be one gotta be 80, 170, 90. Oh my god. This does not look like YZ YZW. The measure of YZ. Is that right? The measure of YZW is 45. I thought it meant XZW. But it does say YZW. It does not look like a 45-degree angle to me. But I'm gonna have to erase all those numbers there. Because I had done it with XZW. But all the relationships that I said are true. Just made a mistake. Okay, so if it does say that Oh, because I left X, Y, Z, W is 45. Okay, WV is 15. WV is 15. VY is 10. VY is 10. Fine. Oh, so then, this is 10. This is 15. And also XWZ. XWZ is on the other side. That's also going to be 45. WXY. WXY. Okay, so these two angles are supplementary. They're same side interior. So 180 minus 45 is going to be 135. Really does not look like it should. XZ is going to be 25 if you add the 10 and the 15 together. And XV is 10. All right. Coordinate geometry, we'll do that after quadrilaterals. But the mid-segment. Okay, so the mid-segment is right in the middle of the trapezoid. Works for all trapezoids, not just isosceles trapezoids. And it is 1/2 of the sum of the bases. That's right there. So if we add like the bases 2 and 10, then what would the mid-segment be? We add 2 plus 10 and divide it by 2, so it's 6. So, and other thing you can see it like that too. You add by the same amount. Okay, so you can do lots of mid-segment questions, and we can do some mid-segment algebra. All right. Properties of kites. Now this is the last one. So make sure you have your kite properties. If it's a kite, then the diagonals are perpendicular. And if it's a kite, then we do have congruent angles on the sides, but not on the top and bottom. That's the difference between a kite and a rhombus. And so what is a kite exactly? It's a quadrilateral where 2 pairs of consecutive congruent sides. So the sides that connect are also congruent, but there's 2 pairs. They're not all congruent to each other. So you can use the properties of kites, and be aware, because of the congruent diagonals, you will have to use the Pythagorean theorem. And like I just said in the property, F and H in this picture would be congruent. So they all add to 360. So then you could find F and H. Oh, look at that. See? Okay. All right. Should we do this last one? Should we? I think you guys can get it. All right, so go forth and do the guided practice questions, especially ones we didn't do. Look at the practice and problem solving, and I will see you in class. Oh, and don't forget to post in the organizer and do your ISO.